All right, in that previous section, we were finding, the area under a curve from, let's say, A to B. We made all these rectangles, right? We added up all these rectangles with delta x on each one. Well, we had the same width each time. Our delta x was b minus a all over n subintervals. Well, if they're all the same, then it's b minus a over n, but they don't have to be the same. You can have what's called the norm of the partition. This is the norm of the partition. So if the norm of the partition is all the same widths, then yeah, delta x would be b minus a over n, but it doesn't always have to be. And we're going to take this, we took the delta x to go to 0. In other words, as the number of subintervals went to infinity, right? So as delta x goes to 0, or the norm of the partition goes to 0, so the number of rectangles goes to infinity, we get a whole bunch of these rectangles, add them all up, because delta x is going to 0, right? We would get the area under the curve. So the limit as the partition goes to 0. So this is the same thing as the limit as delta x goes to 0, or the limit as n goes to 0. All the same thing. And guess what it is? It's an integral. It's an integral from a to b, and we'll talk about that next time. But let's see if we can't recognize it then and make the connection between these two highlighted in yellow. So this would be the area under the curve of x from negative 2 to 3, or I should say the integral, right? Not the area under the curve, because this is not positive. It's not above the x-axis on that whole interval. But what would the Riemann sum be? What would the integral be? Well, we'd have b minus a over n. Notice this is our a, that's our b, right? Our a, our b. So our delta x here would be 3 minus the negative 2 all over n. So our delta x is 5 over n. And as the width goes to 0, in other words, the norm of the partition goes to 0, then n is going to infinity, right? We're making an infinite amount of subintervals. And so note here that our f of x is that x right there. Our f of x is x. And so our ci would be a plus delta xi. And so our ci would be a in this case is negative 2, plus delta x, that's 5 over n I. So ci equals negative 2 plus 5i over n. Okay. So number 3 then, so we would take the limit as the partition goes to 0. That's the same thing as the limit as n goes to infinity of the summation of f of ci delta x, y being 1 to n. So the summation of negative 2 plus 5i over n gets plugged into, remember our function was f of x equaling x, so this just gets plugged into x. So there it is. There's our f of x, which is x right there. And then our delta x is 5 over n. There's our delta x. So we've got the limit n goes to infinity. Let me put the 5 over n in front. And I got negative 2 plus 5 over ni. So we got limit n goes to infinity, 5 over n. Let me break that up. I got the summation of You know what, I could, before I did that, let me go ahead. I could just take that 5 over n through. Let me do that instead. Change my mind on this. So we got the limit as n goes to infinity. Now let me break it up into negative 10 over n plus 25i over n. And so we've got limit n goes to infinity. Let me put the 1 over n in front of negative 10 plus 25 over n summation of I. So that's an n squared. Oops, that's an n squared right there. My bad. And now let's use our formulas. Limit as n goes to infinity. I got 1 over n. And I've got negative 10 constant times n plus 25 over n squared. I was that n plus 1 over 2. So I got negative 10 plus, that'll be 25n squared plus 25n all over 2n squared. So we got 25 over 2 plus 25 over 2n. Now we run that to infinity. That'll go to 0. So I got negative 10 plus 25 over 2. So that'll give us 5 over 2. Okay, and that's the integral from negative 2 to 3 of f of x being x. All right, let's go the other way around now. Change the following into a definite integral. Well, this is, and it's over a partition. So notice they give us the a to b. So I'm like, well, that means I'm going from a to b. Here's my function right there. If you can imagine the CI is your x, so that's like 6x 4 minus x squared. There's your function. And then the width, that delta xi, the width of that, that's your dx. Width of the rectangle is really our dx. And so we've set up the integral there. Do another one. This one's from a to b. So from 1 to 3. And this is 3 over x squared. And the width is your dx there. So we just changed that into a definite integral. Again, be patient with me. Next section, we'll talk about how to do that integral with the fundamental theorem of calculus. But we're going to get into, geometrically speaking, what is this representing? So let's go ahead and graph this integral from 0 to 2 of negative 2x plus 4. And we'll just use our basic understanding of geometric shapes to find the areas for this. So if you notice, our function here is f of x equals negative 2x plus 4. So, if I was graphing that, 0, I'd have 4, 2, I'd have 0, and so on, right? This is a y equals mx plus b, 1, 2, 3, 4. I got a y-intercept of 4, and I'm down to right 1, down to right 1, and so on. And I'm only looking, so let me just graph that from 0 to 2, right? That's our a to b. I'm just looking from 0 to 2. The integral of that. So that is the area that is representing this area under the curve and above the x-axis right there. So you notice we have a triangle right there. Well, we know the area of a triangle. It's 1/2 base times height. And if you notice, our base here is 2. And our height here is 4. And so this area just ends up being 4 square units. How about this one? What does this one look like? Well, here's our function, square root of 9 minus x squared. That's our function. You may have seen it in a different form. Imagine if I had squared both of these sides. I would have y squared equals 9 minus x squared. And if I added x squared to both sides, x squared plus y squared equals 9. So this is a circle. All right, here's my circle formula. X plus h squared plus y minus k squared equals radius squared. So my center is 0, 0 with a radius of 3. Okay, 1, 2, 3, 1, 2, 3. Now, it's actually not the entire circle, because notice it gave us just the square root of 9 minus x squared. So, like, let's say I took this x squared plus y squared equals 9. I solved for y. Square root squared. I'd have the plus or minus, right? Well, the plus is the top side of this circle. The bottom is the negative square root of 9 minus x squared. So I only have this top of this circle. That's square root of 9 minus x squared, right? Or you could just plot a bunch of points if you'd like as well. So we're trying to use areas to evaluate this, right? We're trying to go from, notice it says go from negative 3 to 3. From negative 3 to 3, find this area. Since this is positive, this would be an area, right? So we're trying to find that area. Well, we know the area of a circle is pi r squared, but we only have half the area, right? So it's only half the circle. So we only have half that area. So this area just ends up being 1/2 pi. My radius here is 3. So my area is 9 pi over 2 units squared. That would be the exact area. Got x plus 1 this time. Here's our function, f of x equals x plus 1. So mx plus b, I got a y-intercept of 1, and I'm up 1, right 1, up 1, right 1, up 1, right 1. I'm only going from 0 to 2. So it's just this part of it. I'm trying to find that area. And so what I'm going to do is I'll just go with a triangle, and then I'll do the bottom rectangle. So the area is triangle, top triangle, plus the rectangle. So triangle is 1/2 base times height. The base here in red is 2. The height is 2 plus the bottom rectangle. Let me shade the rectangle on the bottom there in black. Rectangle's length times width, or base times height. Its base is 2, its height is 1. So it looks like we got 2 plus 2. So this area is just 4 total area, right? The total area there is 4. Or you could have done with a trapezoid formula if you wanted to. So you got parallel sides on the left and the right. How about this one? We've got the function 2 minus the absolute value of x minus 1. Let me rewrite that as negative x minus 1 plus 2. So maybe you're thinking about transformations. Here's the square absolute value of x, right? You've got the v. Well, number one, if I flip that over, number two, I'll say, then that's a reflection about the x-axis. So then we would be flipped over like that, right? And then what does that minus 1 do? That would move it to the right one. So right 1. So instead of the red being right at the middle, I go right 1 with it. And then finally the plus 2 on the end would bump it up 2. So I take the green and I go up 2. And there's my graph. And of course you could plot some points too if you wanted to into this. You know, so I'd plug in 1 would be a good one to plug in. 1 comma 2, 0. Absolute value of -1 is just a 1, but then you apply the negative out front, so -1 plus 2 is 1. So 0 comma 1. Do -1 would be another 1. -1 minus 1 is -2. Absolute value -2, 2. -2 plus 2 is 0. Anyways, we could keep going with that. But notice I'm going from -1 to 3. Let's go ahead and put 3 on here. And here's part of that absolute value function graph. Okay. So we're trying to find it from -1 to 3. This is the area under the curve. And so it looks like we have another triangle here. So area is 1/2 base times height. Our base here in red, from -1 to 3, it looks like that's a base of 4, distance of 4. And our height here, our height is a height of 2. So it looks like this area just ends up being 8/2, 4 square units there. So here's some properties we're going to go through, properties of definite integrals. So from a to a of the function, so if you can imagine you have some function, whatever it looks like, from a to a. Well, this width is 0. So it's the height times the width. Well, the width is 0. There's no area there, right? That's why it's 0. You can go from, if you go from a to b, you can flip it around, but you got to put a negative in front of that. Negative, it would be equivalent to the opposite or negative of b to a. Okay. You can split it up as well. Right? So if you have, you're going from a to b, you can also split it up and go from a to c plus c to b, and that's what that's saying right there, right? You can put that k in front of the integral, right? And finally, that last one, plus minus, you could split those up as well, plus minus. Okay, so these are all properties that you have. Let's see if we can't use some of these properties here. So 2 to 2, that's our first one. If I'm going from a to a, it says an area of 0, right? How about from 2 to 4 of 15? So what I would do here is I would put the 15 in front. I'm going from 2 to 4. I still have the dx here. And the reason I did that is because I see right here that is 2. So the 15 stays in front times 2. This just ends up being 30. So I'm using these given rules up above. Let's do the next one. I have x cubed plus 4. So I'm going to split this up. Notice I have x cubed. So this is the integral of x cubed from 2 to 4 dx plus the integral of 4 dx. And I'm going to put the 4 in front and then the dx. Well, the integral of x cubed is the 60 plus 4. The integral of dx from 2 to 4 is 2. So you end up 60 plus 8, 68 on that. This one I would go ahead and multiply through. So I have, I changed my mind. I'm going from 4 to 2 instead of 2 to 4. 4 to 2. I'm going from 4 to 2. That's a little awkward. Let me switch it around because I know my integrals were given from 2 to 4. So I would have to put a negative out front if I'm going to change it from 2 to 4. And then this stuff's the same. So leave that negative out front. I got 2 to 4. Let me distribute the x. I got 2x minus x cubed. And I can take that negative through to both of those actually. So let me take that inside there. Now let me split that up. So I have negative 2 integral x plus, and that's dx, plus the integral of x cubed 2 to 4. So this becomes negative 2, and I go back up here. What's the integral of x? Is the 6 right there. So that's 6 right there. So that's the 6. So it's 6. Plus, then I go up here. What about x cubed? 2 to 4. That's the 60. So I got negative 12 plus 60. So this just ends up being 48 on that one. All right, so this one we got 3 to 3. All right, so this has 0, got to be 0. Right? A to A, there's no width of that rectangle. 6 to 1. Well, I don't have a 6 to 1, I have a 1 to 6. So let me rewrite that, put a negative out front, and then I can change it to a 1 to 6. And then 3 f of x dx. And then what we'll do is we'll put that 3 out with the negative, because I have f of x dx. All right, I have f of x from 1 to 6. See how that's 5? So I got negative 3 times that 5. So that just ends up being negative 15. Negative 15. Let's do the next one. 3 to 6 of f of x. So I'm looking up here and I'm like, I don't have a 3 to 6. I have a 1 to 3. I have a 1 to 6. The other one's a g of x, by the way. But this is just 3 to 6 f of x. Well, if you think about it, if you're going from 1 to 6, right, then wouldn't the integral from 1 to 3 plus the integral from 3 to 6 be the integral from 1 to 6? So I'm going to use that. I'm going to say, all right, well, 1 to 3 plus 3 to 6 will be the same as 1 to 6. All right. And then I go up here and I'm like, well, 1 to 3 is that negative 2 right there. That's the negative 2. The 3 to 6, I don't know this one, so let me just leave it alone. That's what I'm trying to solve for. But I do have the 1 to 6 up here, and that's the 5. And so I just got to add 2, both sides. And so 3 to 6 part would be 5 plus 2, which is 7. Here I've got a 6 to 1, so I'm going to flip that around. 1 to 6 of this f of x minus g of x dx. And I could take that through as well. So it'd be negative f of x and then plus a g of x 1 to 6. And that'd be, let me take that negative out front, f of x 1 to 6 plus g of x 1 to 6. And so I've got negative, and then 1 to 6 f of x. I go back up here. 1 to 6 f of x is that 5. Plus 1 to 6 g of x is that 7. So I got negative 5 plus 7. Looks like that just ends up being 2 right there. Our last one here, we got 1 to 6. 1 to 6 of negative 2 f of x plus 1 to 6 of that g of x. I'm going to put that negative 2 out front of the 1 to 6 f of x. And so we got -2. That 1 to 6 f of x was the 5. And then the 1 to 6 g of x was the 7. So I got -10 plus 7, which is -3 on that. Well, I hope that helps. Thanks for watching, taking notes. See you next time.